All right, so we've come up with some pretty generic inequalities for how probabilities of random variables can be related to their expectation and variance through Markov's and Chebyshev's inequality. And let's see how these can somehow be used in a practical sense for estimating a success probability. So, for example, a legitimate question would be, suppose that we have, this is a classic statistical question and one that you will likely come up against in a lot of situations, which is suppose that we have a situation like a random variable X that is we know it's binomial N and P, but we don't know we don't know what P are. So N is known. We know how many times we get to toss the coin, but we don't know what P is. So simple example would be we are actually tossing a coin. Of course, sometimes it comes up heads, sometimes it comes up tails. We don't know that the coin is fair. We don't want to assume that the coin is fair without knowing that it's fair. That's kind of our initial guess would be it's a fair coin. But the whole premise of statistics is that we want to collect data to verify or to better estimate how something is behaving. So if we were if we were to try to make money off of this, if we went to a casino and we thought, okay, the assumption and the odds and craps are based on the assumption that the dice are fair and that they're all equally, every possible combination is equally likely to come up, as in the examples that we've assumed previously in this course. But what if the dice weren't fair, right? What if they were loaded so that sixes were more likely to come up, for example? But if the casino is still offering us the same odds, if we knew that, we might be able to bet in a way that would allow us to make money. And this is something that people do try to do. It's extremely difficult in craps, as it turns out, because the dice generally are close enough to evenly weighted so that there's no way to get an advantage. But should we take that for granted? Is it totally impossible that there could be a situation that arises where there would be an advantage? Well, of course, there's situations that could arise, but the question is, how would we know it? How much data would we need to collect in order to verify that the probabilities are actually in our favor or at least off from what's assumed? How many times do we need to toss a coin to verify that what the true probability of heads is? Right? If we toss a coin 5 times and it comes up heads all 5 times, that's not enough information to say it's an unfair coin, because there are, even though it's unlikely on any given toss of a coin 5 times that it'll come up heads all 5 times, it's still possible, and it's still probable enough that we shouldn't deviate from our initial assumption. So we're going to estimate, our best guess given the data is that we're going to estimate the success probability just by the ratio of successes, right? X divided by N, right? If we toss a coin 100 times, it comes up heads 55 times, our estimate would be that it comes up heads 55% of the time. But the question is, how accurate is that estimate as an estimate of P? So we call this P hat. Now, what's important here is to realize P hat is a random variable. It's a function of a random variable, X divided by N. Right? So even though after we observe 100 tosses, 55 heads, we can calculate X 55%, 0.55, that's a realization of a random variable. Okay, so it could have been any number of values depending on the data. What are some metrics, or what are some values that we can calculate for this random variable? Well, we can calculate expectation. What's the expectation of P hat? Well, it's the expectation of X over N That's 1 over n times the expectation of x. What's the expectation of x? Well, in a binomial, the expectation of x is n times p. We've already calculated that. Well, we have a 1 over n, and then we have an n times p. Those n's cancel, and we're just left with p. So this is what's called an unbiased estimator. So the expectation of the estimate that we're going to get is exactly what we're hoping to estimate. So the idea is that in some sense, we're pointed in the right direction. The target is the right place, right? Our estimator is unbiased. It's like if we were playing darts and we were shooting at the bullseye, aiming for the bullseye, we're aiming in the right place. We're going to miss left, we're going to miss right, we're going to miss up, we're going to miss down, but we're aiming in the right place. Okay, we're aiming in the right direction. Of course, how good of an estimate, right? How good of a shooter we are. This is, a good analogy here is that we're trying to estimate where the bullseye is, right? So in darts, oh, there you go. So in darts, there's a bullseye, okay? And that's what we're shooting for. Well, this is like the parameter, P, right? And it would be like saying, well, you don't really know what P is, right, in statistics. But you're doing your best to find it. Same thing in darts. You don't really know where the bullseye is. Let's say you're shown the board and then they take the markings away. So you don't actually know where the bullseye is, but you're doing your best to shoot at it, given the information you have. So the first thing, the unbiasedness is saying we're pointing in the right, we're shooting, we're aiming in the right place. And then, but we might be off, way off, right? So how good are we? How precise, how accurate are we going to be? So accuracy is determined by the variance. How much are we varying around that target? So someone who shoots for the bullseye and is, say, all over the place is, yeah, they're centered, or the bullseye is somewhere in between, somewhere, centered on these values, but these values are so spread out that it doesn't give us such a great estimate or such a great idea. Somebody, on the other hand, who is very targeted, very much centered around a small window, has very low variance, would give us a better accuracy and would give us a better idea of what's going on, right? What's the variance of P hat? Well, the variance of P hat is the variance of X over N. 1 over N is a constant, so that comes out as a square times the variance of X. What's the variance of X? It's the variance of a binomial. Variance of a binomial is N times P times 1 minus P. And so we're left with one of the N's cancels. P times 1 minus P over N. Okay, and this is where we can use some bounding, is to say, well, P times 1 minus P over N, what is the bound on that? Well, P times 1 minus P. P is what we don't know. It's an unknown. And P times 1 minus P actually looks something like this. So this can be 0 and 1. And this can be, let's say, up to a quarter. P times 1 minus P looks something like this. So this is the value of P times 1 minus P. So when P is equal to a half, 1 minus P is equal to a half, and P times 1 minus P equals a half times a half is a quarter. That's actually the highest possible value of this variance. So this variance is at most a quarter divided by N, 1 over 4N. So what we can say then by Chebyshev's inequality, so then by Chebyshev's inequality, the probability that our estimated value deviates from the true value by at most, by more than C, is less than or equal to variance of p hat over c squared. And the variance of p hat, we've already bounded by a quarter. So this is, well, 1 over 4n. So it's at most 1 over 4n c squared. So what is the practical implications of this? Well, this actually gets used all the time in political polling. So let's say we have political polls of presidential election. So presidential election, let's take, for example, let's say we're talking about 2024 US presidential election. And at some point in the election, and this is could be a very dated example by the time you're looking at this video. Even though I'm making this video in July of 2024. So let's just call it Biden versus Trump. And what you have is you have various pollsters, polling companies, polling outlets who create polls. And they'll usually list a date on which they took the poll, but then there's a sample. They describe the sample, they describe the margin of error, and they describe, let's say Biden, Trump, and I'll say a spread. Okay. Let me move this over a little bit, not to be so much up against the edge. Okay. So those are the basics. And so what'll happen is you'll have, say, a poll outlet called, call it Rasmussen. They'll say they took a sample of 500 likely voters. They'll characterize their margin of error as 4.5%. They'll say that Biden 47, Trump 49, and they'll call that a spread of Republican +2. Trump being the Republican, Biden being the Democrat. We Ask America. It's another polling outlet. They'll say they took 1,200 likely voters and had a margin of error of 3 points, and Trump 49, no, Biden 46, Trump 49, Republican +3. So what that means, though, so what does that mean? So they're saying they have a 3 point, so it's 3 point margin of error, which is saying that the estimate on Trump is 49%, but it could really, it's really could be anywhere between 46 and 52%, right? There's an error in a variance in that estimate. NBC Wall Street Journal, 890 likely voters, 3.3% margin of error, 47 Biden, 46 Trump. So they say Democrat +1. And then let's say Gravis, 914 likely voters. They say margin of error 3.4. I'm sorry, this should be 3.4. And then 3.3. And they say 49, 48. Democrat +1. Okay. So where do these margin of errors come from is the question. Where do these margin of errors come from? And they come exactly from the variance estimate up here, that the variance bound right here. Okay. We don't know what we don't know what P is. Let's just say P is the estimate for it doesn't matter because it's a symmetric calculation, P times 1 minus P. So you could say we don't know what P is for Trump. So we don't really know the variance, P times 1 minus P, but we know that the variance cannot be bigger than 1/4 times the 1/4 times the 1/4 times the sample size. And so what we also know is that the we want to keep in mind that the 2 standard deviations, what's the chance that we're 2 standard deviations away is relatively small. Even by Chebyshev's inequality, it's 1/2 squared, it's 1/4, but in general, it's much, much less than that. It's believed to be, less than 5% that we're off by 2 standard deviations. So the margin of error reported in these polls is taken to be 2 standard deviations. And we know from what is a standard deviation, right? Two standard deviations is at most square root. So standard deviation is square root of variance. Variance is at most 1/4n. Square root of that is 2 times 1/2 square root of n. So the margin of error is reported as 1 over the square root of the sample size. So in the first case, what's 1 over the square root of 500? If you do the math, see this is 0.045. That's what was the reported margin of error. Second one, 1 over the square root of 1200, 0.029. They reported a 3.0 margin of error. 1 over the square root of 890 is 3.4% as reported, and 1 over the square root of 914 is 3.3% as reported. So that is, first of all, you'll see in a lot of these polls that the margin of error is typically around 3%, and that's because they typically take a sample size of around 1,000, and that's kind of considered to be the sweet spot. That's kind of the norm in polling. You might say, well, why not try to get a better standard of error, a smaller margin of error? Well, in order to have, let's say, a 1% margin of error, how big does the sample size? Does the sample need to be? Well, we know that the margin of error that's reported is 1 over the sample size, and we want a 1% margin of error. So that tells us that the square root of n would have to be 1 over 1%, right, which is 100. And therefore, a 1% margin of error requires a sample size of 100 squared, which is 10,000 people. So even though it seems like you're going from 3% down to 1% is just a couple of percentage points. That's actually really significant. That's a lot of percentage points to go down. And in order to get that, you have to increase your sample size by 10, right? Up to 10,000 people. So it's just too many people. It's too expensive. So that's why pretty much 1,000 is the sweet spot. Going up to 2,000, for example, 1 over the square root of 2,000. What is that? It's about 2.2%. So there is a gain in margin of error, but it's considered to be not worth it, right? So you have to, for all intents and purposes, it's twice as costly. You need twice as many people in your sample to get a relatively small gain in margin of error. So anyway, this is where margin of errors come from in polling. This is how they get reported. And there's a lot more that goes into polling than just this calculation, but this is an application of the inequalities we talked about, in particular, Chebyshev's inequality, and understand and the binomial distribution in political polling and estimating success probability.